Well, hello everyone, and welcome to our presentation. I'm Diego, and I'm going to talk about a project Courier, which refers to real-time optimal batch size prediction for latency SLOs in BigDL, which we're going to explain what it refers to in the future. And first, let's look at the outline of the presentation. So first, we're going to talk about the motivation, so what our project is trying to tackle and the problems it tries to solve. Then I want to talk about the problem itself, how we approach it, and how we gather the data that we use to model the system and conduct the experiments. Then we're going to talk about modeling. So we model the system and some of the response time and accuracy with different models, and then we analyze their fit, and then we settle on the best one for the task. And then based on that one, we build a model, so the Courier, and we conduct some experiments and relate it to other proposed features or models in literature. And finally, we cover future work and we reach the conclusion. So talking about the motivation, so the problem we tackle is basically when you run machine learning tasks, when you want to run it at scale, you want to run it in the cloud because sometimes a single machine is not enough. But oftentimes you run into the case when you run a machine learning task in the cloud, you reach a lot of underutilization of resources. So the task is not using all the resources, which leads to overpaying for the resources that we have. So in those cases, some systems, the best thing to do is to opt for shared infrastructure. So instead of running a single task in the system, you want to multiplex jobs submitted by different users while still giving them the guarantee that the result will be good. So one way to do it is to enforce fair usage between users by giving jobs a maximum time that they can spend running via SLOs or latency limits. And this we want to optimize performance, so optimize hardware efficiency, so that our resources are completely used. And also in terms of deep learning tasks, if we multiplex just from different users, we will also want to provide users statistical efficiency. So what it means is that in deep learning jobs, we want to reach the highest accuracy or result in the smallest time possible, or the highest accuracy given the latency SLO that we're given, and we cannot go past. So since BigDL, the system that we work on, is built over Apache Spark, we're gonna try to model the performance of running deep learning jobs on Apache Spark and in a multi-tenant environment and analyze if that's feasible and what are the consequences. So to sum up, what we investigate how BigDL performs under a multi-tenant environment for deep learning workflows. So for that, we're going to analyze the system utilization, varying the number of tasks and the different parameters. We're going to also analyze the I/O weight. So Spark is famous for doing shuffle and to exchange data between nodes, and that often becomes the bottleneck of the system. So how deep learning tasks relate to this. We're going to also analyze the response time of the tasks. And also, we're going to analyze how BigDL reacts to an increased number of processors. So this is when you have a single task and you scale it to different nodes and they need to exchange data to train the network, how well does it scale? So for that, we analyze its effects on the final accuracy of the model and the response time. And finally, for the models that we build to describe the system, we also compare them using the mean square error of the predictions, actual values, and more generally with the model fit using the R squared coefficient. So to design the experiments, we're gonna vary different factors, as we can see here, so different parameters and see how it will affect the performance of the system. So for parameters, we choose job parallelism, which in Spark is the same as how many job executors distributing across different machines each task will run on. Then we're gonna vary the batch, then the number of jobs from different users running concurrently in the network, in the system, and also the network. So we have a fully connected and then a convolutional network such as the net. We're going to run this on 3 Google Cloud Workers with 16 virtual CPUs and 64 gigabytes of memory each, and then a Spark Master as well. And to design the experiments, we want to use two design approaches. So the first of them, to get an idea of how the system behaves, is the 2K factorial design, in which we choose the two extremes of a factor and we use them to see an approximate idea of how it affects the behavior. And then we're going to do the full factorial design, in which we do all the combinations, so all the different levels of all factors, and then we can extract some insights from there. And then to see the significance of the results, we're going to use the ANOVA analysis, which allows us to do hypothesis testing, but on all four factors at the same time instead of groups of two. So ANOVA stands for analysis of variance and is frequently used to analyze difference between groups. So we're going to conduct the ANOVA analysis to see the differences in the experiments in accuracy and also in response time. So first we see the result of the 2K factorial analysis. So we see, for example, in the first in the top left plot, that different networks scale differently with the batch size, which is also to expect, and also batch size influences accuracy in the same amount of epochs. So as we could see, that's the same as the statistical efficiency of lower batches is bigger than the bigger batches. Then we see that in the right plot that the number of processes, which we define as the total number of executors running in the system, so number of executors per task times the number of tasks. No matter the parallelism and also the number of tasks, the accuracy doesn't change, which is a common factor in synchronous stochastic gradient descent algorithms that Spark uses in this case. And as we can see in the bottom plot, no matter the number of jobs running in parallel in the system, with just one job, we get only 20% usage of resources. But with 5 jobs, we get 60% usage. So it improves, but we can still see that the usage is not as we would hope. Also, in the statistical part, we see that the batch and the network have a p-value that allows us to say that with 95% confidence, we have a significance here. And also the confidence interval doesn't include 0. So here the batch and the network are the only ones that would be significant. So we run the full factorial analysis with all the combinations of all the different factors. And as we can see, the number of jobs increases the CPU utilization. Also, the number of processes, so the total number of executors, improves the utilization, but until a certain point, no matter the batch. And also, since we talked about the shuffle before, we can see that with a bigger number of executors running concurrently, the contention for disk and network increases, and we can see that the time spent waiting for I/O almost increases to 12% with bigger number of processors. And also the response time with small batches decreases, but it stays almost constant no matter the number of executors. And as we talked before, when we distribute a single task between different number of executors, so with one executor, and then we distribute and do two executors distributing the load of the task, we would expect that it would scale linearly. So if you double the number of executors, the response time should halve. But as we can see here, as you add executors because of the overhead of synchronizing every epoch due to the synchronous algorithm and the shuffle that Spark does, the response time just increases no matter the batch size, or it stays the same. And again, we analyze the statistics. So as before, the batch, as we expected, is pretty significant instead of in terms of response time we were expecting. But now the network is not, and we get this product of CPUs and number of jobs, which we call number of processes or number of executors of total in the system. That is also the second most significant, well, or tied with the batch, the second most significant factor in modeling the response time. So it's something we will take into consideration when modeling the system. Now we're going to talk about the modeling approaches that we use. So we're going to model with an ANOVA linear model, then we're going to use queuing theory, a more theoretical approach to it. And then we're going to use machine learning model to model the response time and the accuracy of the system. So first to start, the ANOVA linear model basically is the model resulting from the ANOVA analysis that we conducted before. And it assigns a coefficient to each of the variables and its combinations, and then tries to model the response variables. So as we can see here with the ANOVA linear model, if we try to model the accuracy, we get a quite good fitting model with a 95% R squared coefficient, but the response time has a bigger mean squared error and also just a bit above 60% R squared, which is improvable. And as we can see here, the accuracy is well fit, but the time as you go higher in the number of processes, the linear model is not able to model these pretty well. So we're gonna continue with, we use queuing theory. So we model the system based on the process of training a deep learning model. So each of the executors has to go to the disk, get the appropriate data samples for the training process, then goes to the CPU, process those training samples, then exchanges them through the network, and then goes back to the disk to load them. So this happens as a loop. So we define the response time as the number of loops times the service time of the CPU and the response time of the disk. So which is the disk, it's the CPU. We model the CPU as a queue with no queue and with follows a scheduling policy of processor sharing. So all of the tasks are served at the same time concurrently. And then the disk is the bottleneck of the system, so the I/O follows an MM1 queue, so tasks have to wait for the system. So this is how we model the shuffle that we were talking before. So we model the arrival time at the disk because we model the service time of the CPU as a constant based on the throughput that we saw in the tasks. And then with this arrival rate at the disk, we use the formula for the MM1 queue, and then we try to approximate the service rate of the disk. So we do this. We have the total response time, and the number of loops. So we model this as a 2D linear regression, and we extract the values for this. So as we can see here, then this performs better in terms of model fit than the ANOVA model, but still is not able to appropriately fit this higher number of processes, so the total number of executors with all the tasks. So we're going to go through a different model to try to model these better. So we try different regressors and they settle on these random forest regressors. So we tune each of them using 5-fold cross validation with a grid search for parameters, and these were the chosen ones for accuracy and response time. And as we can see, accuracy is in the lines with the ANOVA linear model, which was also really good, but a bit better. And response time is where we see the bigger change. And as we can see, this points of the response time that we were not able to fit before, and also this now have pretty low errors, so we're able to predict the response time also pretty accurately. So now we're going to talk about our system, Courier. So as we said in the beginning, with Courier, we want to multiplex jobs from different users, and given a latency SLO, so maximum time that a job can spend in the system, we want to guarantee that we can fulfill the SLO, and on top of that, provide the highest accuracy possible to the job. So for this, we create 5 experiments, and we test the performance of Courier against a random batch selector. So a system that chooses the batch randomly, and we compare it against its performance. And then we also compare it against the boosting regressor in terms of prediction accuracy, using the system level features used in literature in other papers to model Spark jobs. And we're going to see how will that translate to the aspect of BigDL, or if we need more features. So with the experiment design, we see that these are the results, which are really similar to the ones we saw before with the random forest regressor. And here in the feature importance, we can see that to model the response time, the processes feature, so the number of CPU times the number of jobs, is the second most determinant feature, which is also goes in line with what we saw in the ANOVA linear model. So this is to also show that the ANOVA linear model was indeed showing the most significant features. And here we see the comparison versus the random scheduler. So we see the response time minus the SLO. So a negative value means that the system fulfilled the SLO and finished before the latency limit. And as we can see, Courier is able to finish before in all of experiments, unlike the random one. And in those experiments in which both fulfill the SLO, Courier shows better accuracy. And in those that it doesn't, it's just because the random one exceeded the SLO to get a better accuracy. So also with the boosting regressor, we compare the error predicting the response time of jobs after training them. We also fit the boosting regressors with grid search and to optimize the parameters, and the average error the absolute error in accuracy. And as we can see, the error in response time, mostly the boosting regressor behaves worse than Courier. And also in accuracy, the boosting regressor just behaves a lot worse than Courier, given the system level features that are defined in other papers modeling Spark jobs. So as for future work in this article, we fixed the number of epochs but for production jobs, it would need to scale and also use the number of epochs as a parameter for predicting the response time. Then we also would like to dynamically update predictions for previous jobs that are already training when a new job arrives, and also allow for online learning or periodical retraining to allow for the model to adapt to new circumstances. So this is the end of the presentation, and now I would really like to thank you for taking the time to take a look at it, and thank you.